Hello students, I'm Arun Surkar and today we will start where we have left in the previous class. That means we are in electrostatics, we are doing electrostatics, and in my first class I have taught you Coulomb's law, its vector form and dielectric constant. So moving on, just after that we have today's topic. You can see here it is electric field, then we will go to the superposition principle, and we must also learn the application of that superposition principle. Within that application we need to know what is electric dipole, and we have to find the electric field for the electric dipole in the axial position and the equatorial position. So this is all about today's class. Let us start from the very beginning, electric field. Now, you can see in Coulomb's law, we have discussed there is a force between two charges, and this force has a peculiar nature. It is actually called central force. It is absolutely same, or not exactly absolutely same, but it is more like to the gravitational force or magnetostatic force. All of these forces have some common features. I am just giving you a glimpse of that common things between the gravitational force, electrostatic force and the magnetostatic force. All these forces, these are the general properties of such non-contact forces. Electrostatic force, it is a non-contact force, just like gravitational force and magnetostatic force. Also it is called inverse square force. Inverse square, this term comes from the factor that F is proportional to 1 by r square. You can remember, you have learned in class 11 that the gravitational force also varies with the distance in the inversely squared to the distance between the two bodies. So hence electrostatic force and gravitational force in this field, in this common ground, they are similar. These all forces are central force. Now there is a general expression for a central force, and central force can be written like that: F is equals to some function of r. F is a function of r, and it obviously acts along the radius. Of course it can be attractive or repulsive depending on these two factors. We can put positive or negative. Positive means going away, negative means coming towards. When the force is attractive, it becomes negative. When the force is repulsive, then we must use the positive sign in order to show the sense that the force is repelling outward direction. So all these forces, the gravitational forces, the electrostatic forces, the magnetostatic forces, are central force. They are the sole function of position vector, and they act along the radius. That means they act along the line of joining. They act along the line of joining. Now we can take this one of that charge at the origin, and then the other position of the other charge will be the position vector, and we denote the position vector with r. Hence we have put r over here. So this is the general form of central force. Also it is a conservative force field. You know what do you mean by conservative force? Conservative force means work done does not depend on path. There is no dissipative force like friction or viscous force like that. So it is entirely conservative. That means here we can find the potential and the difference between the two potential can give the work done in while moving one charge from one point to another. We'll learn it later. Now we just know it is a conservative force, that means work done does not depend on pulse, and we can also get back the work done, and the total mechanical energy will remain conserved. So these are the general features of electrostatic force. Now we'll define one thing, is called electric field or electrostatic field. What do we mean by field? Field is a certain region or certain area where one charge can experience electrostatic force exerted by the other charge. That is known as electric field. Qualitatively, electric field means when we have a charge configuration or a single charge. Let us first consider a single charge is placed in a space somewhere. Now a region around it is developed, where if we bring another charge, anywhere within that region, if we bring another charge, this charge will experience certain force. Now here we are defining these two charges. We can see that we have used different colors for these two charges because these two charges are not categorically different. Categorically they are same, but still, since this charge is producing the field, we will call it source charge. The charge which produces the field is called, say this charge is Q, and this is called source charge. And these charges which you bring from outside in order to see whether there is a force or not, these charges are called test charge. So it's just a name, they are absolutely same. One is source charge which produces the field, another is test charge which you bring in order to test the field. Why should we test? What should we test? We test whether the force is whether the charge is experiencing any force or not. Now it is called the field, the region. Here in the board we are compelled to draw a 2D region, but actually in space it is a 3D region, and if the medium is homogeneous, then it will be obviously a spherical one. You can relate this thing from the very equation of the electrostatic force. That electrostatic force varies as, it's an inverse square force, it varies as 1 by r square. Now whenever r is constant, force will not change. That means there must be a spherical symmetry, isn't that? When r changes, the value of forces changes, but when r is constant, if r is constant, both are r, then the magnitude of the force will be same in all distances which is r from the origin. The force will be same. So hence there is a spherical symmetry, and in the contour or in this space, in this envelope, in this spherical envelope, all the points where we can place the test charge will experience the same force. Now this force which the test charge experience will change when the distance is changed. Hence, over here, if the distance is r1, force will be something. Here, if the distance is r2, force will be something else. So for different positions having different position vectors or different values of r, the test charge will experience different amount of force, but it will experience some force. How far it will experience that force? In this board we have just drawn a hypothetical spherical region. But what is the exact radius of the region where a test charge will experience force, and how far from the central position or from the source charge the test charge will not receive any force? Now theoretically, when F is directly proportional to 1 by r square, it can only be 0 when r is infinity. When r is infinity, r tends to infinity, then F tends to 0. That means theoretically there is an infinite extent of electric field. Theoretically, electric field is extended up to infinity. But practically, we cannot see that influence. Practically, after a certain region, the force becomes so weak so that we cannot perceive the existence of the force, and it will not influence the test charge at after certain distance. Hence, we can imagine a boundary, and after the boundary, this space is called infinity. So, what do we learn is electric field is a space where a test charge will experience certain force exerted by the source charge. That is called electric field. Now, qualitatively it is okay, but quantitatively we need to define electric field. Now, quantitatively it is called electric field intensity or only field intensity. Quantitatively it is called electric field intensity. What do we mean by electric field intensity? Intensity means how forcefully the force is acting, how strong is the force on the on the test charge. What is the strength of the force at that position of the field experienced by the test charge? That is determined by the intensity. Now we can define intensity. Let us write the definition first, then we will explain that. Quantitatively, electric field intensity is defined as the force experienced by a stationary unit positive charge the force experienced by a stationary unit positive charge placed inside any point within the electric field is called electric field intensity of that what? Let me ask you, of that what? The force experienced by a stationary unit positive charge placed inside a point. Now there is both the charges has to be stationary. This is a note. Both the charges, both the source charge and the test charge has to be stationary one. Because a moving charge produces a magnetic field and the accelerated charge produces an electromagnetic field. Only the stationary charge that produces an electric field. So there is a source charge and it has got a field. we have taken another charge, another test charge, and placed somewhere inside the field. Now the source charge is exerting certain field on the test charge, let Q naught be the test charge, exerting certain force to the test charge, and that force in per unit charge is called the electric field intensity. Now electric field intensity belongs to what? Belongs to the source charge or test charge or something else. Look here, if we write the mathematical expression of the electric field intensity, we can find electric field belongs to what? Let us first write the mathematical expression, then we will fill up this thing. Okay. Now we have said that the force experienced by the stationary unit positive charge placed inside a point within an electric field is called the electric field intensity of what? Something we don't know yet. Let me write it in the mathematical form. If we let the distance between the source charge and the test charge be r, here the source charge is q, test charge is q naught. Source charge means that produces the field. Test charge is very small amount of charge which doesn't influence